So it's a little intimidating following Jan, but actually this is a very good sequence of talks, because Jan mostly talked about how you learn skills efficiently, and I'm mostly going to talk about how you figure out which skills to learn. But before I begin, I want to make a very short plug. There's a group of maybe 100 or so people interested in doing artificial intelligence combined with robotics and sort of mainstream AI venues that have gotten together and set up this mailing list, just AI-robotics at google.com. That's run by Alessandro Safiotti, who I'm sure many of you know, and we're sort of trying to coalesce to get a big enough critical mass to be able to do interesting and useful things. One of the things that we're running is a workshop at AAAI, and the deadline's in like 5 days, so there's plenty of time. All right. Okay, so this talk is mostly about hierarchical robot control. And so I always like to start out with a photo of a cool robot. So this is the PR2. This is the robot that we have at MIT. You could substitute in an iCub if you'd like. And what's really cool about this robot is that, in some sense, the hardware problem for non-very exciting, for not very dynamic tasks is solved. In the sense that that robot is capable of doing more or less anything that you want to do, provided it's not super dynamic. And anything that we as roboticists could ask it to do. But we just don't know how to program it. We don't know how to get that robot to do the right thing. So I would like to be able to build a robot like that I could say, hey robot, I would like some tea. And the robot would say, well, George likes sugar in his tea, and go to the kitchen and notice that there's no sugar in the kitchen. And then decide, well, the way to get sugar is to go to the corner shop, which is down the road, but in order to do that, I should pick up some money on the way out the door. Right, this robot is physically capable of doing that, but we just don't know how to efficiently program it to do that. And it seems clear that what you need is some sort of hierarchy. That is, on the bottom level, you want to be doing low-level control and perception, because we're roboticists, and we always have to do that. There's no escaping it. But we'd like to also be able to do some sort of high-level planning. We'd like to be able to reason over relatively abstract things. And so if you look at what the kinds of things that we're manipulating at each of these levels look like, at the low level, you've got this kind of continuous, noisy, local and partially observable sensory motor space, which for the purposes of this talk I'm going to call swampy. And this is a difficult space to deal in, because you deal with these very high-dimensional continuous objects. But it has the advantage of being real, in the sense that this interaction with this space is actually something that exists. It's grounded. You can interact with the world that way. And then higher up, you have this sort of discrete, abstract, symbolic thing that perhaps we'd like to get to, where the robot can make decisions like, well, George wants sugar in his tea. We don't have any sugar, so I should go to the corner shop. And that's very nice to deal with, because that's discrete and abstract and symbolic, and we've got 50 years of AI that worries about doing those things. But it's sort of fictional, in the sense that that's not necessarily grounded, or it's our job to build that thing such that it's grounded. And the real question that I'm interested in addressing is what goes in the middle, what goes between these two things. What is the connecting tissue that gets you from this low-level thing, which I call swampy, that gets you from your swampy level to the high-level thing, which I call crispy? Okay, so this talk is about a way of getting from swampy to crispy, broadly. And the sort of claim that I'm going to try and make, I'm going to try and convince you of, is that the way to do this is by building action abstractions, by building skills, just as Jan talked about. And the advantage, the thing about skills is they're these sort of components of behavior, right? They perform this low-level continuous control, but you can treat them as discrete things. You can give them a label, and you can reason about their effects and about their actions, and maybe about their parameters. And there's some evidence that humans organize their behavior this way. So broadly, if you look at human babies, they go through the sequence of development. This is a baby learning to grasp an object. So that happens at about 4 to 6 months, quite reliably at 4 to 6 months. And the exciting thing about that is it opens up this new set of things the baby can do. Right? Before it was able to grasp objects, it kind of mostly just sort of sits there. But afterwards, it can grab things, it can pull them towards it, it can manipulate them, it can do interesting things with them. So what you get is you get this sequence of action learning problems where after the baby's learned each action, its behavioral scope increases drastically. Okay, so that's one reason why you might want to be able to pull these things out. The second one is specialization. This is David Beckham. It's a relief to be able to give a talk somewhere where I can refer to what he plays as football instead of soccer. But if you look at a lot of human activity, what it boils down to is doing something like isolating a particular piece of behavior that you may wish to learn, and then applying a learning algorithm, much as the algorithms that Jan has talked about, to become progressively better at that thing. So on the one hand, you have the question of how do you do learning once you've got the problem. On the other hand, you've got the question of what problem do you learn? So at some point when David Beckham was 12 or 14 or however old football players are when they do this, he decided that long ball kicks are his thing. So, you know, the game of soccer is a big game. There's a lot of stuff going on in it. There's all this back and forth. But somewhere in there's a component that was isolated and thought to be interesting, and then explicitly practiced. Explicitly practiced, in this case, for decades. And a lot of human specialization is built off this sort of thing, right? It's not just that you can do learning. It's that you can pick what you do learning at. And the third property, which I think is most interesting, is the simplification property. So this is a Rubik's Cube. This is a relatively hard combinatorial search problem. It has an average depth of 20 and a huge branching factor if you treat it as classical search. But there's a group of people, there's a sort of community of people who think about these things. They're called speed cubers. And a speed cuber can solve a Rubik's Cube on average in 10 seconds or less. And most of that time is actually taken by executing the moves. And the way the speed cubers do this is they have this library of what they call algorithms. This is kind of mildly embarrassing, but they call them algorithms. And what they are is they're motor skills. They're things that say something like, move the color in the top left to the bottom right while not changing any of the other colors on one face. Okay, so the algorithm books that speed cubers have, there are about 40 of these things. But it turns out that once you've memorized these things, this problem as a search problem becomes almost trivial. That is, the time it takes to do the search in this problem is insignificant compared to the time it takes to actually solve the cube. And if any of you have tried to solve a Rubik's Cube from scratch, you know that that's not a small transition in difficulty. Okay? So, and just because you're a computer science audience to some extent, the other way that I like to talk about this is that skills are like functions. If you ask what is the single most useful and non-obvious idea in all of programming, it's building functions. It's almost unreasonable to ask someone to write a reasonably large-sized program without using functions, without breaking it into chunks that they can reuse, that they can sort of get right and then put away and then reuse when they need to. So skills are kind of like functions. We're gonna have a robot that can solve problems and then retain pieces of that solution that it can just redeploy when it needs to. So there's a lot of questions around this sort of large-scale question of how we can construct and use hierarchies. Skill hierarchies. This has a lot of components. I'm mostly going to talk about how we can discover skills, how we can efficiently learn skills. Jan knows how to do that better than almost anyone, so I'm not going to talk about that. But then, as you go sort of further down the list, you get to how do you build a true hierarchy out of these things. So the first part of my talk, I'm going to talk about how do we discover skills, and for the last part, I'm going to talk about some preliminary work about how we use those to produce symbolic descriptions of the world. And the central hypothesis of this is that behavior is modular and compositional. What that means is that most of the behavior that you go through in your everyday life involves repetitions of other pieces of behavior that you have done before. That is, you know, when you get out of bed in the morning and you brush your teeth and then you put on your clothes, these are all things you've done before. Your behavior is broken up into these little pieces. They recur, so solving them and reusing them makes hard problems easy. So for this talk, mostly I'm going to focus on building up from the sort of bottom up, from a reinforcement learning framework, the ability to deploy a robot like that. And I'll show you at the end a demonstration of this robot. The robot videos come kind of late in this talk. I'll show you an example of this robot solving one task and then extracting component skills from the solution and then deploying them in a new task to solve it faster. And then at the end, I'll talk about a little work on symbol synthesis for these sorts of systems. So I'm just going to very briefly talk about background. I guess Jan mostly went through this already. The sort of theoretical framework I'll use for this is reinforcement learning, where you have an action. This is our very realistic robot over there. You can take actions in the world, you get back a state, and you get a reward. And you're trying to maximize the discounted sum of rewards. So you're not trying to maximize reward at this step, you're trying to maximize rewards in the future. And the two objects that I'll be talking about are policies, which are mappings from state to actions, that bit, and value functions, which are mappings from states to expected rewards conditioned on a policy. Now, normally you solve, in reinforcement learning, you solve a single problem. You frame a problem this way, you solve it, and then you're done. But in hierarchical reinforcement learning, we're concerned with breaking this problem up into subproblems. So we'd like to create and use these high-level macro actions. And then each subproblem also turns out to be a reinforcement learning problem, so this is nice and neat. This is a nice, clean theoretical framework that provides a theoretical basis for everything I'm going to build from now on. And in particular, I'm going to use the options framework, which is one particular way of expressing hierarchical reinforcement learning. So that kind of looks like this. You have an agent. Once again, we have a highly realistic robot. It can move up, down, left, or right, as all very, very realistic robots can. And this is going to cruise around in some environment. And it's going to have some algorithm in it that when it encounters a state that it thinks it may wish to create an option to reach it, perhaps by, in this case, doing a graph cut. Over here, it's built a sort of local model of this domain and realize that there's a sort of a small cut over there will partition the domain into two pieces. It creates a second copy of this problem, moves the target to the sort of target state over there, and then learns to solve that original problem, that derived problem. And then what it does is it takes this thing, which we'll call a skill or an option, and it adds it to the robot's behavioral repertoire, so now the robot can go up, down, left, right, or it can move directly to that target. So a bit more formally, an option O is a policy unit. It contains an initiation set. That's all of the places where you can execute this piece of policy. A termination condition, which tells you when you're done, and an option policy, which is the little arrows which tell you what to do in all the states in your initiation set so that you reach the termination condition. And so maybe 5 or 6 years ago, we knew how to do this in very small, discrete domains, like the domain I've just shown you. We had a good set of algorithms that could do this in those sorts of domains. But we didn't really know how to do it in high-dimensional continuous domains. So what I'm going to talk about for most of this talk is a sequence of algorithms that let us do this on robots. So the first algorithm is skill chaining. This is about discovering skills in continuous environments. The second one is abstraction selection, which is about picking out skill-specific abstractions. This is the thing that lets us scale up. Then I'll talk about a very fast way to break trajectories into skills, and then I'll show you some cool videos. So the question behind skill discovery is, how does an agent autonomously create new skills? Now in a discrete sort of domain, you could maybe build a graph representation of your domain and run a partitioning algorithm to get a goal state. But that's not going to work in a continuous domain because you never see the same state twice, and it's not clear what a goal looks like and all of that sort of stuff. You need a region, not a state, for a goal. So the most obvious thing to do, which is what I did, is to say that the goal of creating an option should be to solve some task. So let's start out with some task that the agent needs to solve. It needs to go from that little X all the way to this light bulb and say, okay, let's learn a skill to do that. And it turns out that in most interesting domains, you can't learn a skill to do that from everywhere. You can only learn a skill to do that from a small region, reliably. So let's call that our option. And then let's say, okay, the next time you reach after we've learned that option, the next time you reach that option, we'll create a skill to reach that option. So now we've created our first skill, it reaches the end of the goal, and we've created our second skill, which reaches the initiation set of the first skill. And if you repeat this process, you get a chain. And the idea here is that you can, from anywhere in the domain, you should be able to execute a sequence of options that takes you from the beginning to the goal. Okay, and if you actually apply this to a domain, you get sort of relatively interesting stuff. So this is the pinball domain. This is an elastic ball bouncing through an environment. Its state is x, y, x dot, and y dot, and it'll change colors when it changes skills. So what's happened here is we've broken up a relatively hard, long control trajectory into little pieces. This is pretty cool. Boing. Little pieces that can be very accurately represented and modeled. So I am the only person who has ever really played this domain, but this is a lot better than I am at this. It's the world champion, if you like. So that trajectory looks like this. I've broken it up into skills for colors. And if you look on the top left over there, my pointer is not being very effective. If you look on the top left, you'll see the initiation set for the final skill, the skill that reaches the goal. It's a 4D set, so I've summed over the x dot and y dot trajectories, where it's very light, it means that you can execute the skill from any particular velocity in that state. Where it's very dark, it means you have to be at specific velocities in order to be able to execute the skill. So the one in the top left, you can see, there we go, you can see just over there, you need to be at quite specific velocities in order to be able to run the skill, whereas once you're in here, you can run it from any particular velocity. Now, what's interesting about this is that if you compare it to a flat reinforcement learner, two things happen. The first one is that very quickly, so this red line is a flat reinforcement learning, the blue line is skill chaining. Very quickly, within about 50 episodes, you can do much, much better than trying to solve this whole problem in one go. And you can get much, much lower variance. So what that means is by breaking this hard, long problem that contains many, many careful twists and turns to avoid hitting walls or bouncing off the walls in the correct way, by breaking that up into a sequence of things that we can model very well, we can get an extremely good solution, much better than if we tried to solve the thing from scratch. The second thing is, if you look at this green line at the top there, the green line tells you what happens when I take those skills away from one agent and give them to another. So we have an agent that doesn't know how to solve this problem but is given acquired skills that it's just gifted by another agent. And on the very first trajectory, you do better than the flat learning solution. Right? And very, very quickly, you get to an extremely good solution. What that tells you is that those acquired solutions make this problem easy. Okay? If you pull out these skills and you keep them, the next time you approach this problem, it's very easy to learn to sequence them. It takes almost no effort at all. So, and I'm kind of going through this quickly because the robot videos are more interesting. So the point of all of this is that we have this sort of basic algorithm that tells us how to create new skills, and we can use it to improve performance. And the gain is really due to representational advantage. That is, you don't have to represent this whole policy as one thing. You can break it up into a sequence of things, sort of adaptively break it up into a sequence of subproblems that you can solve well. But scaling up is really not feasible for an algorithm like that. It takes about 10 episodes to learn each skill, which is not reasonable for a robot. Also, when you scale up the number of dimensions, reinforcement learning becomes exponentially harder. If you look at successful examples of real-time robot learning, what you often find is that the reason that this is successful is that someone has showed up beforehand and said, these are the 5 or 6 state variables you need to care about in order to learn this accurately. Some engineer has showed up and said, okay, if you're going to learn to juggle, you need to care about the X and Y position of the ball and some other stuff. And this feature set is typically very small because the larger it gets, the harder the problem gets, roughly. So one way to model this is to say that you've got your robot there, and then you have an abstraction pair. You have a sensor abstraction, so all of your data goes through this abstraction. It's filtered down from this very large robot space into a small space. And then you have some policy, which sends actions to a small motor abstraction, which tells the robot roughly what to do. Now, if you're just interested in learning a single skill, maybe you're just interested in solving a problem, it's totally feasible for you to write this down. But in the case where we're trying to get the robot to figure out which problems it should solve by itself, it's not feasible for us to intervene and tell it which state variables it should care about. So how do we get around that? How do we create these kind of abstractions that are specific to the skills that we're trying to learn? So the way that I approach this problem, I should say that there are methods that can, in principle, learn that all from scratch. They could, in principle, figure out what state variables you need from scratch. It's just that the data complexity of those methods is much longer than, is much too high for us to feasibly use on a robot. So I kind of came up with this intermediate solution, which is if we have a library of abstractions, that is, if I program 30 or 40 or 200 abstractions into the robot in advance, then can I ask it, when it learns a skill, can I ask it to pick out the appropriate abstractions that it can learn that skill efficiently? So this is called abstraction selection. So in other words, given a trajectory, which set of basis functions, because I should have mentioned earlier, we're doing linear value function approximation just for this example. Which set of basis functions should I use to represent the reward function represented by the trajectory I've just experienced? So if you do machine learning, this is familiar to you as a model selection problem. It's all about how you represent a function given some input and output pairs of that function. Which model should you select to represent it? And it turns out that the simplest thing that you can do, the simplest thing that anyone ever does, is called Bayesian information criterion, which is effectively to fit a model, write down the maximum likelihood of that model, and then take off a penalty for the size of the number of basis functions in your abstraction. What's nice about this is that this is an approximation to a log likelihood of the data given the model, so you can plug it into probabilistic methods further up to do something like select the most likely abstraction when you are 95% sure that you have the right one. So just to clarify what the inputs and outputs here are, the models are, when I say model, I mean an abstraction. When I say input, I mean states, and when I say output, I mean the value function. This value function thing is not observed. You get little r's, but the value function is a big R, is the sum of the little r's over time. So you have to do a little bit of algebra to be able to keep sufficient statistics over this sum of things that you don't get to directly see. And then we're going to do BRC plus a little bit of magic to get a probability for each abstraction over time. So I'm just going to show you another toy domain. This is the continuous playroom. And this is the kind of domain that's hard for reinforcement learning, but shouldn't be because it's kind of silly. So here we have some set of objects and effectors. The effectors are a hand, an eye, and a marker. And the objects are red and green buttons, a ball, a light switch, and a bell. And the idea is that if you want to solve this task, if you can move your eye and your hand over an object, you can interact with that object. Interacting with the light switch switches the lights on or off. If the lights are on, you can interact with the green button, which switches the music on, or the red button, which switches the music off. If you manage to get the music on and the lights back off, and you put your hand and eye over the ball and your target marker over the bell, and you interact with the ball, it fires the ball at the bell in the dark with the music on, and it scares that little monkey. So I should at this point mention that I did not invent this domain. But it's the kind of domain that's interesting because it consists of these sort of small interactions. The options are things like moving your hand over this button, and these are very simple things, right? To a human, this looks silly. Of course, you just move your hand over the button. But there are something like 120 state features in this domain. So how do we figure out that only the difference, the x and y difference between the button and your hand are the important things? How do we figure that out? And so very simply in this case, I generated a whole bunch of possible abstractions. And it turns out that it takes about 6 or 7 experiences with one of those options to figure out which abstraction you should use. So just to show you this graph, the red line is what happens if you try and learn in this domain with no abstractions. So you're still given skills, but you have to learn them in the full state space. The black line is what happens if I give you the skills and I give you the skill policies. So this is like an upper bound. And the dash line, the dash green line, is what happens if I give you the skills and I give you the abstractions and you have to learn them. So that's also like an upper bound. The blue line is what happens if I give you the skills, but I don't tell you which abstraction to use, and I ask you to wait for 5 episodes or until you're 95% certain. So that vertical line over there is the threshold where I let the agent use abstractions. And you can see that pretty much immediately you switch from one regime to another. Pretty much within 1 or 2 episodes, you switch from this sort of long, hard, complicated task to I can solve this task pretty much as easily as if I was given the abstractions and the options in advance. And just to get a handle on the size of that y-axis, that's times 10 to the 5. So these are very, very large differences in the amount of steps this kind of thing takes. So what's interesting about that is the sort of ability to combine skills with the appropriate abstractions. So this, I think, is part of one of the key things that's going to potentially make learning reasonable. This is an approach for solving high-dimensional problems. Right? Many problems really are high-dimensional if you take them monolithically. Right? If you try and solve the problem of getting through your whole day as one problem, you really do require many hundreds to possibly thousands of variables. But if you can combine something like skill chaining, which breaks up your day into skills, and then abstraction selection, which figures out which small number of variables you care about for each skill, you can solve each one of those in a reasonably small amount of time. So as a sort of exercise, I mapped out my day just kind of abstractly, first thing in the morning I get up and I brush my teeth. And when I brush my teeth, I'm not thinking about what I'm going to wear or where my keys are or how to drive my car from my house to the building I work in or how to navigate the building I work in, which if you've ever been to it is non-trivial. I'm just thinking about brushing my teeth. And then after I brush my teeth, I forget about brushing my teeth and I just think about what I'm going to pick to wear. And I don't think about any of the other variables I care about in the whole day. So the real point here is that behavior, by virtue of being modular and compositional, is piecewise low dimensional. That means you can pick out pieces of your day and say, during this piece, I only care about a very small number of things. That's what makes learning feasible, and that's what makes scaling up feasible. So the final piece that we need in order to be able to do this on a robot is skill acquisition by demonstration. So when I say demonstration, I mean from a trajectory. For part of this, there'll be a human in the loop, and for part of this, there won't be. And the idea here is that with skill training, you kind of learn these skills kind of one piece at a time. You learn one, you learn where it works, and then you make that a target, and you learn the next one, you learn where it works, and makes that a target. If you're going to be able to do this on robots, you have to be able to take a trajectory and just cut it into skills, and assign each one an appropriate abstraction. So CST is about taking those trajectories, breaking them into skills, selecting an abstraction for each skill, and then when you have multiple trajectories like that, merging them back into a tree to say, okay, the way to solve this problem, depending on where you start, you have to follow some branches. Eventually, you converge into a sort of main line, and then you solve the overall problem. So CST does sort of all of this in one step. It's a principled statistical way for picking out the abstractions and figuring out when to switch skills based on when the abstractions change. So the inputs here are trajectories of states and rewards, and the output is a segmentation into skill abstraction pairs. Again, we're going to use linear value function approximation. And then we have to think about when we want to switch skills. Well, we want to switch skills, like in pinball, if the value function becomes too complicated to represent in one go, maybe we want to break it up. Or otherwise, the relevant abstraction changes. So it turns out that there's a statistical tool for handling this called Changepoint detection, and that involves a hidden Markov model. So very briefly, the hidden states in this hidden Markov model correspond to the abstraction that you should be using. The observed states correspond to the reward that you see, given the state that you're in. And the two statistical quantities we care about are the probability of seeing a reward given a state conditioned on an abstraction. So if you're using the hand to button abstraction, what is the probability that you would see this piece of data? And the other one is how long on average do you expect these skills to last? So this is a geometric distribution on how long skills last, and that's nice and natural because we can say, I expect skills to last 50 time steps, and then you can just write down the parameters of that distribution. The exciting thing about this is it's a hidden Markov model where all of the parameters are known. We don't have to do any learning. We can just do inference on this model. So we can apply something like a Viterbi algorithm and just pull out the segmentation of this trajectory. So I'm going to show you a toy example. On the top, you're going to see some data that I'm just generating from fake linear models. And on the bottom, you're going to see a particle model of where the last change point should be. So that's a probability distribution, a discretized probability distribution. On the top, you see the data sort of shows up, and it's linear but noisy. And then when you get a transition, you see that you get a spike in where the segmentation should go. And the final thing is there are 3 linear models here, and they break at that point and at that point. So what we're going to do is we're going to do that, but we're going to do that on the robot's data, and the underlying model we're representing is a value function. So there's some math, which I'm going to skip because it's boring. And then finally, you get a segmentation for several trajectories, and you merge them in a sort of stepwise fashion. You look at the probability of the last 2 things being from one skill, and if that probability is above some threshold, you merge them, and you keep doing that down the tree until you run out of places where they could merge. So if we apply this to pinball, these are me demonstrated trajectories for pinball. What you see is that it cuts it up into skills. There are no abstractions here. This is just cutting it up where the value function becomes too complicated. It cuts it up into skills on the top and on the bottom that sort of represent natural boundaries in where the trajectory occurs. And then you can merge those into a tree which says, well, on the right-hand side, some stuff happens, and on the left-hand side, some stuff happens. Then once you reach here, you follow the same piece of the tree all the way through. And if we put this into the learning system, it learns to solve this thing in like 2 episodes because it has these very nice handy skills. But pinball is sort of boring, so let's do this on robots. So I got my collaborator Scott Kindersma, he's the gentleman in the yellow shorts, to pilot this U-bot through this very just small sort of toy domain. The idea is that the U-bot goes up to this door and pushes it open, and then cruises around the corner here, and then pushes on a sort of button on the end of a panel. And you can see these colored dots. These are visual features available to the robot. It's the difference between its torso and those colored dots, and the difference between its hand and those colored dots. So what happens when you run CST on this is it pulls out skills that look like pushing open the door and approaching the panel and pushing the button. Right. And the reason it does so is because the abstractions change. So this is the sort of trajectory segmented from that demonstration. The first part of the trajectory says, walk up to the door. And there, the abstraction that you care about involves the difference between your torso and the door. So when you're walking up to the door, you don't care about where the orange dot is, you don't care about where the yellow dot is or where your arm is, you just walk up to the door. Then you switch to the small blue piece is the abstraction where you push the door open. So there you care about the distance between your hand and the door, but not where your torso is or anything like that. And in the green and the yellow, you're sort of looking at different dots as you're turning around this corner to guide your behavior. Then you go through the corner and you push the panel at the end. So because these things are very low dimensional, those abstractions are like 3 to 4 real variables each, it turns out that you can use a very small number of abstractions to reproduce this thing without any learning. I think we asked for 9 out of 10 successful replays. And of course, if you wanted to, you could apply learning to this in a much reduced state space. So there's also been some follow-on work with a more sophisticated statistical model with a student at UMass called Scott Neekum. So the idea here is that this is a PR2, and Scott's going to guide this PR2 through the what we call the census task, where the PR2 has to grab a pen and mark whether it's male, female, or robot on the wall. So this is Scott. This is a different Scott. This is Scott Neekum demonstrating the task. And then what happens is that piece of task is broken up into things like picking up the pen. So this is segment 1, which is in the marker coordinate frame. This has to do with picking up the marker. And here we've sort of moved all these things around, right? What's nice about this is because you're abstract to the positions of the other things in the environment, you can transfer this skill. Come on. All right, so that was all kind of really, that was all working up to this sort of system. So I'm just going to show a couple of videos now of a robot autonomously solving one task, this task over here. It's called the red room task, and I'll explain it in a minute. It's going to solve that task, it's going to get a solution to that task, and then it will pull component skills out of that solution and retain them. And then we will put it in a new task and ask it to solve that new task. And we will measure whether it can solve that new task faster than when it does not have acquired skills. So this is the red room environment. I'm just going to start playing because it takes a little while. This is the U-bot. What the U-bot is allowed to do is walk up to interesting things. And then it has a set of sort of basic motion primitives, like it can stick out its arm and move it left or right or up or down, or it could lean forward or retract its arm. And what it's going to do is basically by reinforcement learning, it's going to learn over time that if you press that button there an odd number of times and you you unlock the door, and then you pull that handle, this door will open. Once the door's open, you can cruise through that door and approach that switch. And if you push the switch, you get 1,000 points. Hello. Anyway, so this is the optimal solution to that problem, learned by the robot. Here you can see what it sees through its kind of binocular, through its sort of stereo vision. And it takes about 5 episodes, so it takes about an hour for the robot to figure out the optimal way to do this. This hour is very stressful because if you look up there in the top right, you can see my feet. I'm standing on a desk holding a stick that is holding the robot's cable out of its way. This is quite stressful to do for an hour at a time. But it learns, it does the right thing, roughly. The robot looks a bit like it's helicoptering, but actually all it's doing is whenever it reaches a new place or it performs some action, it just takes a look around the environment to see what has changed. Okay, so it presses that thing and it gets 1,000 points, and the task is over. And then we can take this solution trajectory and we can break it into component skills using CST. So we get skills like pressing the button. And pulling the handle. And pushing the switch. The robot's kind of slow because it's dynamically balancing, so everything wobbles as it moves. You can't move it very quickly, unfortunately. So one thing to note about those skills is the robot could always do that, right? It could always press a button, right? But what it had to do in order to do that was it had to solve some very long, complicated task, during which pressing a button was just one of the many sequences of actions that it took to do this. So it solved this whole task monolithically. It solved this whole long thing, and it did that. But now we've pulled out pressing the button or pulling the handle. So if you put this robot in a second task and you ask it to solve it, when it walks up to something like a handle without acquired skills, it has to solve this whole long sequential problem from scratch. In fact, this is only a component of the extremely long sequential problem that it's solving from scratch. Right? It just happens to be that it's going to stick around in front of this thing for long enough to work it out. But when the robot has acquired skills and it walks up to the handle, it knows exactly what to do because it knows how to deal with handles. Right? So this little subproblem is solved. We can just redeploy the solution to this little subproblem. And we can redeploy that solution partly because it's abstract, in the sense that abstraction selection has thrown away all the variables you don't care about. And that lets you execute that in isolation on that little sort of piece of the wall. So if we put this in a second task where here the robot has to press the green switch an odd number of times, then press the button, that opens this door, goes through the door, pulls the handle, that closes the door again, revealing the button on the other side, and then it can go up to the button and press it and solve the task. If we do this on the left, you see without skills, and on the right with skills. If you watch the robot on the left, it's kind of dumb in the sense that you can see that it's sequencing a whole bunch of very primitive things. It walks up to buttons and it tries a bunch of very sort of simple motor primitives. But the robot on the right just sort of approaches things and approaches a button and pushes it. It knows about buttons. It's learning at a higher level than the robot on the left. And consequently, because it's learning at a higher level, hopefully it figures out how to solve this task much more quickly than the robot that is not learning at a high level. So it's probably going to happen is the robot on the right is going to cruise over and press that button. No. I think door's open. All right, so this goes on for a little bit of time, but the overall result is that you can roughly halve, in this particular instance, you can roughly halve the amount of time it takes to solve that task by using acquired skills. So what's interesting about that is that, well, I mean, first of all, we've scaled this sort of thing up to a mobile manipulator. So what that means is that that robot is doing skill acquisition on a long, continuous stream of high-dimensional data. That is, that trajectory that it's getting to segment is this big sort of trajectory full of all the values available to the robot. It's breaking them up into small abstract skills, and it's allowing you to reuse them by itself. And they're suitable for further learning. You could apply any policy search algorithm to them, and you would be able to improve them, although we didn't actually do that. And it's suitable for deployment in further problems, partly because those skills are abstract. Right? Pushing a button doesn't have to do with where in the environment the handle might be. And the sort of general thing, this is just scratching the surface of being able to do this. But the general idea here is that if you can use these acquired skills to improve a robot's problem-solving abilities. You can take a problem that can solve a robot that can solve some set of problems, let it solve them, and then through the kind of solutions that are used to solve them, through retaining components of that, you can then get it to solve harder problems. So there's this sort of open-ended aspect to that. And what's interesting there is that the problems that are solved were solved because they were useful solving a previous problem. Right? So if we say something like, what problems does the robot want to solve? Well, it wants to solve problems in the future like it solved in the past. What that means is that the components, solutions to problems that are solved in the past will be useful for problems in the future. All right, so briefly I'm going to talk about, after all of that, I'm going to talk about some work on symbol acquisition. How am I doing for time? Okay. All right. I'm going to zoom through some work. This work is very preliminary. Some of it is so preliminary as to be almost imaginary. But we'll go through it pretty quickly. The question I'm interested in asking here is broadly, where do symbols come from? So this is Shaky the robot. This robot was built in the 60s, and this was the first kind of AI robot. This robot did high-level planning as well as low-level execution, and it drove a lot of the application of AI technologies after it. But the way it did that is it sort of modeled things in this language called strips, where you had a high-level symbolic description of the domain, and then you had controllers that executed that description at a low level. So strips kind of wrote everything down in terms of the symbolic representation, using operators, states, and goals. And the operators ground out to a motor skill. They ground out to a piece of code that you can run. But you also have parameters and predicates. And it's kind of not clear where those are from. It's not clear how those ground out. What usually happens is that someone shows up, as what happened with Shaky, and thinks hard about this problem and says, well, the right logical description of this problem looks like this. And here are the pieces of motor control that I can write down that will execute the actions that come out of my planner. And here are the pieces of perceptual code that will ground out the symbols that I need in my planner. And then they try and run it, and inevitably it doesn't work. And so they go back, they loop, until there's a sort of mesh between the symbolic description they've chosen and the motor skill and the sort of low-level, the swampy components of the robot system. Obviously, the solution is not really satisfactory. So one way to think about it is to say, well, what happens if we take a symbolic description of the world and we ask what motor primitives might we want for that description of the world? So we can design the symbolic description. We can create motor primitives to manipulate symbols. So this is a giant typing error. Motor abstractions don't manipulate symbols, but they manipulate the world such that the symbols describing the state of the world change. And you can describe this as symbol first. What this does is it sort of privileges the symbolic description. It says the symbolic description is the true thing, and then we will create the rest of the system around it. And there are some people that do sort of similar things, not all the way up to robots, but similar things. But it still begs the question, where do the symbols come from, and how do we know that they represent the right stuff? And so what I'd like to advocate is the opposite direction. I'd like to be able to say, skill first. Let's take some motor primitives, which we've already shown kind of that we can learn from experience, and ask what symbolic descriptions are necessary to plan with them. And the motivation here is that skills are real things in that they're grounded in your sensory motor interaction. You can get them from solving problems. They're low level, they're swampy, and symbols are imaginary in that you get to invent whatever symbols you would like in order to plan with the skills that you have. All right, symbols are things the robot gets to hallucinate in order to be able to reason about what it can and cannot do, because behavior is ultimately the goal here. So the first question we should ask if we're trying to invent symbols is, what is a symbol? So if you ask a logician, they will say that a predicate symbol is a name for a set of swampy states. That is, the predicate symbol holding a can is the set of states that the robot could be in such that it's holding the can. Right? This is a kind of circular definition, but this is how language works. But you could imagine there being an infinite, in fact, size number of swampy states that could be represented by the single symbol the robot is holding the can. You could imagine the robot's holding the can and moves this way a little bit or that way a little bit, or it's holding the can in different places and all these sorts of things. It's also a test. You should be able to evaluate the symbol. I should be able to tell you whether the symbol is true in the current state or not. Otherwise, the symbol is not useful. It's not grounded. So we can define a propositional symbol as the name associated with a test. And that test comes with a set of states. So that's basically a classifier. Right? This should be familiar to machine learning people. It's a classifier. It's a thing that says, for which states in the world is this thing true? For which swampy states is this thing true? And so it's worth differentiating between the set of states, which is an extensional representation, it's an infinite list of states, and an intensional representation, which is the particular classifier that I use to represent that set of states. Perhaps for simplicity, imagine that you use a decision tree. Okay? You have a decision tree that's true for some states and false for other states. It's true for an infinite set of swampy states, and those are the set of states that your symbol refers to. But when you say symbol, what you're really talking about is the decision tree itself. It's a very compact functional representation of an infinite set of swampy states. And if a symbol is a classifier and it supports the following operations, union, which is an OR, intersection, which is an AND, and subset, which is like logical implication, then we can build an algebra of those classifiers. We can take two classifiers, we can AND them, and we can get a new classifier. Right, this is just like doing a symbolic operation. You can take a predicate, you can AND them, and AND it with another predicate, and you get a third predicate. So the question is, what are we going to use these symbols for? And my contention here is that they're abstractions an agent invents in order to be able to plan and thereby act. So let's start with a low-level swampy SMDP. So we've got a set of states, a set of options we can take, a reward function, and a probability transition. And we'd like to be able to build the necessary symbols to allow us to reason about whether or not action plans in that SMDP are feasible or not. So what that means, a plan is just a list of options from a state set Z. So a state set Z is also a symbol. And a plan is feasible when the probability of the agent being able to execute it is 1. Right, so this is a very strong condition, but this is the classical planning condition that says you must guarantee for me that if I give you a plan and you tell me that I can execute that plan, then I execute that plan and it works. And it's satisficing if the probability of it reaching a goal state is 1. So if we kind of step back, we can say a symbol refers to an infinite set of swampy states. And symbolic planning finds a satisficing plan by manipulating these classifiers, by taking these compact representations of the states and doing operations on them. And it turns out that you can write down some obvious candidates for the symbols you may wish to use to evaluate whether a plan is true. For one thing, you could ask about the precondition of an option O. You could say, let's form the set of states that refer to that option's initiation set. That is the set of states where I can run that option. You also need to be able to compute the image of an option given a set of states. So if I'm in some set of states and I execute an option, I should be able to give you a classifier that refers to the states that I have a non-zero probability of landing in subsequently. And it turns out that these sets of states are sufficient for planning in any SMDP. That is, if you represent the initiation set and the image operator of an option, I can tell you whether any plan formed with those options in that SMDP is feasible. Okay, so that's sufficiency. It also turns out that there are SMDPs for which this is necessary. That means no other set of symbols, except ones that can be reached using operations on these, can tell you whether any particular plan is satisfying. Okay, so these symbols are the necessary and sufficient symbols for planning using your required skills. What's very exciting about that, at least to me, is that it tells you that symbols are not really a degree of freedom. People think that you could define the symbols that you want to think about some domain, and you can define the motor skills, but actually the agent and the motor skills in the environment completely specify the symbols that you want to use to reason about plans for that agent. It also has this interesting implication that the right symbolic description of a domain depends on the skills available to the agent. So here's a toy example. It's our very realistic robot again. So this robot is navigating through a room. In some cases, it has a controller that takes it to the centroid of one of the walls it can see. And in another case, it does wall following and goes to the corners. Right? The images of these two sets of operators are completely different. Okay, so what our theory tells us is that you take the same domain and the same agent and you give it different skills, and the symbolic description of that domain has to change completely. And of course, because we've defined these states very precisely, we now know exactly what they mean, it turns out that you can learn them. That is, here's a sort of toy example with a decision tree, which makes it a very toy example in this case, from the Continuous Playroom domain, where I've asked the agent to learn a symbol corresponding to the initiation set of interacting with the bell. And you could write that symbol down. You could say that decision tree corresponds to the set of states where the light is on and both the hand and the eye are over the bell. Okay? That's how we might describe it. But to the agent, that decision tree is all it needs. It needs to be able to have that decision tree and do operations on that decision tree, and it can do planning. So to summarize, the environment and goal and actions specify the symbolic representation we need completely. That representation is learnable because it's now precise and clear which exact symbols you want. And all this learning enables planning. That is, what we're going to do is we're going to start with an agent that doesn't know enough about the world to plan. We're going to do skill acquisition, pick up a bunch of skills, and then create the necessary symbolic representations to plan using those skills, all from the bottom up. And so in this case, the sort of skill first gives you leverage on how your hierarchy should look. Skill acquisition really drives symbolic representations. To make that point a little bit clearer, this is the part that's nearly imaginary because I have the idea, but I haven't actually written any code yet. We can create something called a skill symbol loop. That is, say you have a set of skills. We now know that those skills determine the symbols you need to plan in this domain. And those symbols describe a discrete MDP. So if you apply a skill acquisition to that discrete MDP again, you get another set of skills. Okay? But now we know that when you change your skills, you have to change your symbolic representation. So now you have a hierarchy of actions, but you also have a hierarchy of symbols. Right? You get high-level actions. That means you need a higher-level set of symbols to reason about those actions. You can keep doing this. You can go all the way up. So here's a very silly example. Say you've got this robot, and the PR2, and it can pre-grasp something. It can grasp it. It can lift it. It can move its arm to above one of the two boxes, and it can release it. If we go through the definition of the symbols that we need, we can write down the symbols we need to plan using those actions. Right? We need to be able to tell whether we're above the box with the apple. Sorry, this is a sort of toy domain where there's two boxes. One of them has an apple in it. Whether we've pre-grasped the apple, whether we've grasped the apple, whether we've got it in the air, whether the arm is above one box or the other. And then if we ran a skill acquisition algorithm on this, we might say that, well, pre-grasp, grasp always happen one after the other. So let's collapse them into something that looks like grab apple. Okay, a standard discrete skill acquisition algorithm will do that for you. So now our new skills are grab apple, move the arm to above the box, and drop the apple. And that results in a much smaller set of symbols. Have you grasped and lifted the apple? Is the arm above B1 or B2? Is the apple in B1 or B2? And then if you run that again, you might land up with a single parameterized skill that says something like move the apple to. And when you do that, you see that you only need two symbols. Is the apple in B1 or is the apple in B2? So what happens here is as we go up in this hierarchy, as we apply skill acquisition one after the other, the symbols become more general. And a formal way of stating that is they refer to a larger set of swampy states. And they become fewer. You don't necessarily get fewer skills, but you should if you use a reasonable skill acquisition algorithm. And the idea here is that at some point you top out into a basic description, that you top out into some description that can't get any simpler. And perhaps that might be what a logician would refer to as the correct description of the domain. And hopefully what happens is the robot details will sort of wash out. And they'll be at the bottom. They'll have to do with whether you can grasp and what you can reach and what you can't reach. And at the top will just be a nice, clean, logical description of this problem that we can solve at a top level and then ground down into acquired motor skills. So just to return, this is my last slide, just to return to the overall question of how you get from swampy low-level control to crispy high-level control. One answer is you do skill acquisition, and then you learn the symbols that you need to represent those skills and plan with them. And then you do skill acquisition again, and then you get the symbols that you need to learn and plan with that high level of skills. And you do that all the way until you run out of abstraction. And then you have a hierarchy. All right, I think that's all I have to say. Any questions? Did I?